I'm here to add yet another model to your list. So yes, this has been a project, or is a project I should say, that is a collaboration between CSU, the Colorado State University, the University of Warwick, the US Department of Agriculture, and Linköping University in Sweden, where I'm from. It's been funded by the DHS, the Department of Homeland Security of the US. What we've done is we've developed a infectious disease outbreak simulation model capable of modeling, for instance, foot and mouth disease in the US. And what I'd like to do is to briefly tell you something about the model, a brief description of it, and more or less just let you know that we exist and what we are working on. So yeah, the model's called the disease outbreak simulation, and you'll notice that it's missing an FMD in there. As I said, it's intention to be able to model other diseases as well, but we've mainly been using it up until now to evaluate, and while we have been developing it, we've had foot and mouth disease very much in mind. We call it the US DOS for short. And as I said, it's a national scale, premises level simulation tool for modeling infectious disease within the United States cattle population mainly. And when I say national scale, that of course means, since we're talking about the US, in practice almost continental scale. The model consists of two main components. There's the kernel-based local spread component, as well as a long-distance spread component, the transmission via a stochastic shipment generation process built in. So constructing this kind of model for the US comes with a number of challenges. And I thought I'd tell you about the challenges, point them out during my brief description of the model, and also tell you about how we've overcome these challenges. Hopefully, some of you might be interested in the techniques we've been using. So, starting out with the population that we are using to model. The US cattle population consists of over 100 million animals spread across around 815,000 premises, the largest of which are bigger than 100,000 animals. And you'll probably notice that I'm not going to refer to them as farms, but premises rather, because I don't think you can call a feedlot of 100,000 animals a farm, I guess. So here comes challenge number one. We don't know where the farms are precisely. There is no data for that. What we know is the number of farms per county divided into a set of discrete size classes. But of course, to be able to model an infectious disease spreading between individual premises, we also need to know their locations. So what we've used is another tool called the Farm Location and Agricultural Production Simulator, which more or less uses a set of predictors such as geographical predictors, anthropogenic predictors such as roads, closeness to roads and closeness to urban areas and so on, climate variables, and aerial photography in combination with the data that exists on the county level to build a probability surface across the US for that's sort of describes predicted farm occurrence. And then we use that probability surface to simulate stochastic realizations of the actual farm or cattle premises population. And I'd like to point out that we have not developed this method, but we have used it, and we have used it to very good effect. It was developed by Chris Burdett and colleagues. It's been published. So that's the farm population part and the challenges with that. So onto the local transmission component of the model. It's a pretty standard one. Some of you will recognize this from Matt Keeling's paper from 2001. We have an infection rate between every infectious and susceptible premises, controlled by or dependent on the respective premises' transmissibility and susceptibility, which are in turn functions of the number of animals on that farm, so the size of the premises, as well as a distance dependence function, the distance kernel. I have the kernel formulation here. I'm not going to go into any detail about that. So the problem, the next challenge with this is that, of course, we don't have any outbreak data for the US, and we need to parameterize our kernel. With a lack of outbreak data, what we've had to do is to use the UK 2001 outbreak data to parameterize our kernel. And this is an ongoing work. What's shown in that figure is the current best fit of the kernel. I just put it up there for illustrative purposes, but we are currently working on refining this this parameter fitting. So it's an ongoing work. Yes, and of course there are a bunch of other model parameters. I think I'm going to skip over those. So a challenge then with this, when we have this kind of premises to premises level model, is that we need to evaluate infection or transmission occurring every time step in the model. And when you have close to 1 million farms, that becomes quite computationally intensive. So to solve this problem and not create a model that is completely useless, we could either go with an approach where we introduce additional approximations into the model, such as having a cutoff for the kernel, like not evaluating transmissions via local spread for longer distances than some number. But we were very reluctant to do that if we didn't have to introduce additional approximations. So what we did was to build upon another method introduced by Matt Keeling, where the landscape is divided into, where the population of farms is divided into squares. And then we have a hierarchical transmission process where we evaluate if transmission can go from an infectious farm first into a square containing a bunch of susceptible farms, and evaluate if any of those farms can become or would become infected. And only if that is true, we go into the square and do the actual individual transmission events. And I realized that this is the UK. It's just there to show you roughly what it looks like. Yes, and this method improves speed by around a factor of 500 for the US. Depends on the population, but for the US it's around that improvement, and the approach has been published quite recently in PLOS Comp Bio, if you are interested. Yes. So we also have this shipment transmission part of the model, and cattle shipments are generated continuously throughout the simulation, and it's based on a premises size-dependent shipment rate, which in turn is based on a number of state and county level variables, as well as a distance dependence similar to the local spread kernel. And just as with the local spread, the parameters for this needs to be fitted, of course. And for that, we have a separate model called EuFMD, the US Animal Movement Model, which has been published a version of in 2013, but we are working on version 3 right now, and version 2 is almost published. So it's a continuous improvement of this model as well. And maybe it sounds simple to just estimate parameters from shipment data. The problem is that shipment data doesn't exist either, or very limited shipment data exists. So what we have to work with is a 10% sample of all the transports that cross the state border to estimate these parameters, which means that we have to be pretty innovative in how we scale that up to a complete shipment network, and EuFMD can do that for us. Yes, so those were the 4 challenges we've met, well, 4 of many challenges that we've met during the development of this model and how we've solved them very briefly. Come see me and talk to me if you want to know more details about those. So I thought I'd just mention something about what we are doing with this model. And first of all, we took a look at importance of shipment for spread of foot and mouth disease, just out of curiosity. So on average, every farm will send a shipment every 3 years or something like that. So shipments are relatively rare, but what we can see when we look at them is that they are pretty important for the spread of, or the proliferation of the outbreak, which may not be a big surprise, but it's quite interesting the way that happens. So I'm not going to go into the details of the scales of these figures. I don't think I have time for that. I realize they look a bit wonky, but there is a good reason for why they look the way they do, and I can explain that in detail if anyone's interested. But the important part is that the maps show if you seed in a county, we have seeded 100 times in each county, and for that specific county, the color represents the 97.5th percentile of the number of infected premises after seeding 100 times in that county. Does that make sense? I hope so. So this map shows the results for seeding in every individual county 100 times with shipments and no control whatsoever. And this is the same simulations, but with the shipment component taken out. And of course, there are fewer infections without shipments. But what's interesting is that still the percent of direct transmission, the percent of transmission events that are caused by local spread are practically close to 100% throughout the entire country. So still of course, the number of transmissions caused by shipments are very few, but they bring the outbreak to a new area where it can start a new small outbreak. As I said, not a big surprise maybe, but we were interested to see what kind of role shipment plays in the US. So for control strategies, we have in the model the possibility to include movement restrictions, depopulation, that is culling, vaccination, and also we model dangerous contacts through the model. So US-DOS allows us to add constraints for these different control strategies as well. All right. And control scenarios are parameterized with input from the USDA. So we work pretty closely with the experts there to sort of try to develop a good idea of what would be an actual strategy used by the USDA in case of an outbreak. And the scenarios we've tried out so far is depopulation of both infected farms and dangerous contacts, together with a state-level movement restriction, as well as depopulation of infected farms and vaccination of dangerous contacts, together with the state-level movement restriction. And what we can see is the no control map from the previous slides. For reference, together with the culling strategy, culling of disease, and the vaccination strategy. And they are quite similar, but what we can see from these maps is that the vaccination strategy is gives slightly lesser outbreaks, and also the response is quite different for some specific counties. So where the outbreak starts will have an effect on what is the optimal control strategy. Now, I'd like to say that these are very preliminary results, so don't take this as a recommendation. So to conclude, US-DOS allows us to effectively simulate outbreaks and evaluate control strategies with, in a very large populations, without the exact locations of the premises, and with very limited information about the shipments. And what we can see from these preliminary results that we have is that control shifts the national scale outbreak patterns, and shipments are very uncommon, but also very, very important for the proliferation of the outbreak. So I'd just like to thank all involved in this project, the USDA and DHS for funding, and I'd like to thank you and EuFMD for this opportunity.